Welcome to the world of remote sensing and GIS. In this video, we'll explore the foundational concepts that make remote sensing such a powerful tool in modern science and engineering. Remote sensing allows us to gather information about objects or areas from a distance, typically using satellites or aircraft. This technology is essential for monitoring the environment, managing resources, and understanding changes on Earth. Whether you're interested in agriculture, forestry, geology, or meteorology, remote sensing provides invaluable data for analysis and decision-making. Let's begin our journey by understanding what remote sensing is and why it matters. Main objective of studying remote sensing in GIS is to introduce students to the basic concepts and principles of these technologies. By the end of this course, you'll have a solid understanding of the principles behind remote sensing in GIS, including how data is collected, processed, and interpreted. These skills are crucial for anyone looking to work in fields that require spatial data analysis or environmental monitoring. Let's move forward and see how these objectives translate into real-world outcomes. Remote sensing is the science and technology of obtaining information about objects or areas from a distance, typically without making physical contact. This is achieved by detecting and measuring electromagnetic radiation reflected or emitted from the target. Devices like cameras and scanners act as sensors, while platforms such as satellites or aircraft carry these sensors. The term remote sensing was first used in the United States in the 1960s and has since evolved to include various techniques like photogrammetry and photo interpretation. Today, remote sensing is widely used in Earth observation, thanks to advancements in satellite technology. Platform in remote sensing refers to the vehicle or structure that carries the sensor. Common platforms include aircraft and satellites, which enable us to capture data over large areas and in difficult-to-access locations. The choice of platform depends on the application, required resolution, and coverage area. For example, satellites are ideal for global monitoring, while aircraft are used for more detailed localized studies. The development of platforms like Landsat 1 in 1972 marked a significant milestone in Earth observation, making remote sensing data more accessible and useful for a variety of applications. Remote sensing works by detecting the unique characteristics of electromagnetic radiation reflected or emitted by objects. Each object has its own signature, depending on its material and environmental conditions. Sensors capture the radiation in different bands, and the data is then processed either automatically by computers or manually by experts. The processed information is used in various fields such as agriculture, forestry, geology, hydrology, and meteorology. This process allows us to monitor changes, assess resources, and make informed decisions without direct contact with the target area. Remote sensing has a wide range of applications across different sectors. In agriculture, it helps monitor crop health and predict yields. In forestry, it's used to assess forest cover and detect changes over time. Geologists use remote sensing to map landforms and identify mineral resources. Hydrologists monitor water bodies, while meteorologists track weather patterns and climate change. Environmental scientists rely on remote sensing for pollution monitoring and disaster management. The versatility of remote sensing makes it an indispensable tool for modern science and resource management. Electromagnetic radiation is the foundation of remote sensing. It is a form of energy that travels through space or matter, carrying information about the objects it interacts with. This energy can be described both as a wave and as particles called photons. The behavior of electromagnetic radiation is governed by Maxwell's equations, and it exhibits properties like wavelength, frequency, amplitude, and polarization. Understanding these properties is crucial for interpreting remote sensing data, as different materials interact with electromagnetic radiation in unique ways. Electromagnetic radiation can be understood in two ways, as a wave and as a particle. As a wave, it consists of oscillating electric and magnetic fields that travel perpendicular to each other. The wavelength, frequency, and velocity of these waves are related and determine the type of radiation, such as visible light or microwaves. As particles, electromagnetic radiation is made up of photons, each carrying a specific amount of energy. This dual nature explains phenomena like the photoelectric effect and is fundamental to how sensors detect and measure radiation in remote sensing. There are four main elements of electromagnetic radiation: frequency or wavelength, transmission direction, amplitude, and plane of polarization. Frequency determines the color in the visible region, while amplitude relates to the energy carried by the wave. The direction of transmission helps in locating objects, and polarization provides additional information about the surface properties. These elements are essential for extracting meaningful information from remote sensing data, as they influence how different materials reflect, absorb, or emit radiation. When electromagnetic radiation interacts with matter, it can be reflected, absorbed, transmitted, or emitted. Each material has unique spectral characteristics, which means it interacts with radiation in a specific way. For example, a green leaf appears green because it reflects green wavelengths and absorbs others. These interactions are the basis for identifying and analyzing different materials using remote sensing. By studying how radiation is absorbed or emitted at different wavelengths, we can infer the composition and condition of objects on Earth. At the atomic level, electromagnetic radiation can cause electrons to move between energy levels. When an atom absorbs radiation of a specific wavelength, its electrons are excited to higher energy states. Conversely, when electrons return to lower energy levels, radiation is emitted. This process is fundamental to understanding why different materials have unique spectral signatures. For instance, visible light is often emitted by excited electrons, while infrared radiation is associated with molecular vibrations. These principles help us interpret remote sensing data accurately. Electromagnetic radiation is divided into different regions based on wavelength, including gamma rays, X-rays, ultraviolet, visible light, infrared, and radio waves. Each region has unique properties and applications in remote sensing. For example, visible light is used for color imagery, while infrared is useful for temperature measurement and geological studies. Microwave radiation is often used in radar systems. Understanding these regions helps in selecting the appropriate sensors and interpreting the data they collect. Remote sensing utilizes specific spectral bands to capture information about the Earth's surface. These bands include near-ultraviolet, visible, near-infrared, shortwave infrared, thermal infrared, and microwave. Each band provides unique insights such as vegetation health, soil moisture, or surface temperature. The choice of spectral bands depends on the application and the type of information needed. For instance, reflective infrared bands are influenced by solar reflection, while thermal infrared bands are dominated by ground emission. Visible and reflective infrared remote sensing relies on sunlight as the primary energy source. The sun emits electromagnetic radiation with a peak in the visible region, which is reflected by objects on the Earth's surface. By measuring this reflectance, we can gather information about surface materials and conditions. Some systems, like laser radar, use their own energy sources. Thermal infrared sensing, on the other hand, detects radiation emitted by objects themselves, which is related to their temperature. Thermal infrared remote sensing measures the radiation emitted by objects due to their temperature. This is particularly useful for detecting heat patterns, such as in urban heat islands or volcanic activity. Microwave remote sensing includes both passive and active methods. Passive microwave sensors detect natural emissions, while active sensors like radar send out signals and measure the backscatter. These techniques are valuable for monitoring soil moisture, vegetation, and even ice cover. In remote sensing, images can be analog or digital. Analog images like photographs display continuous tones or colors. Digital images, however, are made up of small cells called pixels, each with a specific value representing intensity. The process of dividing an image into pixels is called sampling, while converting analog values to digital is known as quantization. Digital images are easier to process, analyze, and store, making them the standard in modern remote sensing applications. Pixel or picture cell is the smallest unit of a digital image. Pixels are usually square for easy processing, but other shapes like triangles or hexagons can also be used. The size of each pixel, known as spatial resolution, determines the level of detail in the image. Smaller pixels provide more detail but increase data volume. Proper sampling is essential to ensure that important information is not lost, and the Shannon sampling theorem guides the optimal sampling frequency. Quantization is the process of converting analog image intensities into discrete digital values. The number of quantization levels affects the accuracy of the digital image. Too few levels increase quantization error, while too many can lead to unnecessary data and noise. The goal is to choose a quantization level that balances accuracy and data volume. This ensures that the digital image accurately represents the original scene without excessive storage requirement. Information extraction and remote sensing can be categorized into 5 main types: classification, change detection, extraction of physical quantities, extraction of indices, and identification of specific features. Classification involves grouping image data based on spectral, spatial, and temporal information. Change detection identifies differences between images taken at different times. Physical quantities like temperature or elevation can be measured, while indices such as vegetation index are computed from satellite data. Finally, specific features like disasters or archaeological sites can be identified. Both humans and computers play important roles in interpreting remote sensing data. Humans excel at qualitative analysis and recognizing complex patterns, while computers are efficient at processing large datasets and performing quantitative analysis. Combining both approaches often yields the best results. For example, computers can enhance images, making it easier for experts to interpret geological features. Interactive systems allow humans and computers to work together, improving the accuracy and efficiency of information extraction. Expert systems are computer programs designed to mimic human interpretation skills. These systems use knowledge from experienced interpreters to extract information from remote sensing data. They are particularly useful for tasks that require specialized expertise, such as geological mapping or disaster detection. By automating certain aspects of interpretation, expert systems can save time and reduce costs, while still benefiting from human knowledge and experience. Image interpretation is the process of extracting qualitative and quantitative information from images, often in the form of maps. This includes identifying the shape, location, structure, function, and relationships of objects. In satellite remote sensing, interpretation can be done using single images or stereoscopic pairs for 3D analysis. The goal is to translate raw image data into meaningful information that can be used for decision-making in various fields. Image reading is the basic form of interpretation, involving the identification of objects using elements like shape, size, pattern, tone, texture, color, and shadow. Measurement involves extracting physical quantities such as length, height, or temperature from images, often using reference or calibration data. These processes are essential for converting raw image data into actionable information, whether for mapping, resource management, or scientific research. Image analysis goes beyond basic interpretation by examining relationship between interpreted information and real-world phenomena. The results are often presented as thematic maps, which highlight specific features or conditions, such as land use, vegetation, or geological structures. Thematic maps are valuable tools for planners, scientists, and decision makers, providing a clear visual representation of complex data. While remote sensing provides valuable information, ground investigations are often necessary to validate and refine interpretation results. Ground truthing involves visiting the actual location to verify the accuracy of image interpretation. This step is crucial when establishing interpretation keys or checking preliminary maps. Combining remote sensing with ground data ensures that the final results are reliable and useful for practical application. There are 8 key elements used in image interpretation: size, shape, shadow, tone, color, texture, pattern, and associated relationships or context. Each element provides unique clues for identifying and analyzing objects and images. For example, the size and shape help distinguish between different types of trees, while tone and color can indicate vegetation health. Understanding these elements is essential for accurate and effective image interpretation. Size of an object in an image can be measured using the photoscale, which relates image dimensions to real-world distances. Shape refers to the outline or form of an object as seen from above. Recognizing specific shapes such as the circular crown of a conifer tree or the irregular shape of a deciduous tree helps in identifying different features. Industrial sites, airports, and harbors can also be distinguished by their unique shape. Shadows in images can be both obstacles and aids in interpretation. While they may obscure details, shadows also provide information about the height and shape of objects such as towers or bridges. Tone refers to the range of gray levels in an image from white to black. Different materials reflect light differently, resulting in unique tones. For example, dry sand appears white, while wet sand looks black in panchromatic photographs. Color is a powerful tool for distinguishing between different types of vegetation or land cover. Color infrared photographs or false color images can reveal details not visible in standard images. Texture refers to the pattern of repeated small features in an image. For example, grasslands have a smooth texture while forests appear coarse. Texture analysis helps in differentiating between various land cover types and understanding surface condition. Pattern refers to the regular arrangement of objects, such as rows of houses or fields. Recognizing patterns helps in identifying features like orchards, highways, or urban layouts. Context involves understanding the relationship between objects and their surroundings. For example, the location of a river relative to nearby vegetation can provide clues about the landscape. Both pattern and context are essential for accurate image interpretation. Spatial resolution defines the smallest object that can be detected by a satellite sensor. It is usually measured in meters and represents the area covered by a single pixel on the ground. Higher spatial resolution means greater detail, allowing for the detection of smaller features. For example, a sensor with 1x1 meter resolution can detect cars, while one with 1.1x11 kilometer resolution may only show large villages. Choosing the right spatial resolution is crucial for meeting the needs of specific applications. Spectral resolution refers to the ability of a sensor to distinguish between different wavelengths of electromagnetic radiation. It is defined by the number and width of spectral bands the sensor can record. Fine spectral resolution means narrow bands, allowing for detailed analysis of specific features, while coarse resolution covers wider bands. The choice of spectral resolution affects the type of information that can be extracted, such as distinguishing between different types of vegetation or minerals. Radiometric resolution is the sensitivity of a sensor to differences in signal strength, or how finely it can distinguish between variations in reflected or emitted energy. It is usually expressed in bits, with higher bit values allowing for more precise measurements. For example, an 8-bit sensor can record 256 levels of intensity per pixel, while a 7-bit sensor records 128. Higher radiometric resolution improves the ability to detect subtle differences in surface features. Temporal resolution refers to how frequently a satellite sensor can capture images of the same area. This is important for monitoring changes over time, such as crop growth, forest cover, or urban development. Some satellites can revisit the same location every few days, while others may take weeks. High temporal resolution is especially valuable for applications like disaster monitoring or agricultural management, where timely data is critical. Landsat is one of the most widely used remote sensing satellite programs. Launched in 1972, it has provided continuous Earth observation data for decades. Landsat satellites carry various sensors, including the Multispectral Scanner MSS, Thematic Mapper TM, and Enhanced Thematic Mapper Plus ETM Plus. These sensors capture data in multiple spectral bands, enabling detailed analysis of land cover, vegetation, and water body. Landsat's long-term data archive is invaluable for studying environmental changes over time. Spot System pour l'Observation de la Terre is a French satellite program launched in 1986. It features two main imaging systems, HRVIR and vegetation. HRVIR provides high-resolution data in visible and near-infrared bands, while the vegetation instrument is designed for monitoring plant health and land cover. Spot satellites have played a key role in environmental monitoring, agriculture, and urban planning, offering detailed images for a wide range of applications. Advanced Very High Resolution Radiometer (AVHRR) is a sensor flown on NOAA satellites. It captures data in visible, near-infrared, and thermal infrared bands with a spatial resolution of 1.1 kilometers. AVHRR is widely used for global vegetation mapping, land cover monitoring, and agricultural studies. Its ability to provide daily coverage makes it ideal for tracking changes in large-scale environmental conditions, such as droughts or deforestation. India's remote sensing program began with the launch of IRS-1A in 1988. Since then, several satellites have been launched, including IRS-1B, IRS-1C, and IRS-1D. These satellites carry sensors like LISSIII, which captures data in visible, near-infrared, and shortwave infrared bands. The program has advanced with the launch of IRS-P6 RESOURCSAT-1, featuring high-resolution cameras and the ability to provide stereoscopic imagery. Indian remote sensing satellites are extensively used for agriculture, forestry, and resource management. RSP-6, also known as RESOURCSAT-1, is a highly advanced Indian remote sensing satellite launched in 2003. It carries the LISS-IV camera, which provides high-resolution imagery in 3 spectral bands and supports stereoscopic imaging. The LISSIII and a YFS sensors offer additional coverage in visible, near-infrared, and shortwave infrared bands. These capabilities make IRSP-6 a valuable tool for detailed resource mapping, agricultural monitoring, and environmental studies. Remote sensing satellites are equipped with a variety of sensors, each designed for specific applications. Multispectral sensors capture data in multiple wavelength bands, while panchromatic sensors provide high-resolution black and white images. Thermal sensors detect heat emissions, and radar sensors use microwaves to penetrate clouds and vegetation. The combination of different sensor types allows for comprehensive monitoring of the Earth's surface, supporting a wide range of scientific and practical applications. Selecting the appropriate sensor for a remote sensing project depends on the application, required resolution, and environmental conditions. For example, high-resolution sensors are ideal for urban mapping, while multispectral sensors are better for vegetation analysis. Thermal sensors are used for temperature studies, and radar sensors are valuable in cloudy or forested areas. Understanding the strengths and limitations of each sensor type ensures that the collected data meets the project's objectives. The future of remote sensing is bright. With advancements in sensor technology, data processing, and artificial intelligence, new satellites offer higher resolution, more spectral bands, and faster revisit times. Machine learning algorithms are improving the accuracy and efficiency of data analysis. As technology evolves, remote sensing will play an even greater role in addressing global challenges, from climate change to disaster management and sustainable development. Despite its many advantages, remote sensing faces challenges such as data volume, processing complexity, and the need for ground validation. Large datasets require significant storage and computational resources. Interpreting data accurately demands expertise and sometimes field verification. Overcoming these challenges requires ongoing research, improved algorithms, and collaboration between scientists, engineers, and end users. Remote sensing impacts our daily lives in many ways, from weather forecasts and disaster alerts to navigation and resource management. Satellite imagery helps farmers optimize crop yields, urban planners design smarter cities, and emergency responders assess damage after natural disasters. As remote sensing technology becomes more accessible, its benefits will continue to expand, making our world safer, more efficient, and better understood. Summary: remote sensing and GIS are transformative technologies that enable us to observe, analyze, and manage the Earth's resources from a distance. By understanding the principles of electromagnetic radiation, sensor types, and data interpretation, we can unlock valuable insights for science, industry, and society. As technology advances, the potential applications of remote sensing will only grow, helping us address global challenges and build a more sustainable future.